Hello everyone! Today I want to talk a bit about my progress with the graph variational autoencoder and want to share some learnings regarding the generation of new molecules. All of the code is available in a new GitHub repository, which is linked in the video description. Molecule generation is a pretty tough topic, as first of all the space of new molecules is huge, and secondly several validity constraints need to be considered when generating new molecules. I read a couple of papers to get an overview of where the current research is, and I quickly want to share two valuable resources here. First of all, Petar Veličković has published some slides about GNNs for molecules on his website. In this presentation there is also a section about generative graph models. This section provides a pretty structured overview of different papers. Prominent examples are, for instance, the junction tree variational autoencoder or the graph variational autoencoder. Then I found this survey on deep generative models for graph generation. It's a bit more general and doesn't focus on graph neural networks, but summarizes the whole research field. The methods for generating graphs can be divided into one-shot and iterative approaches. One-shot methods output the whole molecule representation in one run. As these plots show, we can see that these models, for instance using a fully connected network, directly output the matrices, such as the adjacency matrix. Iterative models, on the other hand, sequentially build a graph. For instance, the first node is added and then the information such as the node embeddings are updated and the next node is added and so on. And the unit of each element that is added can also be larger, for instance predefined substructures of a molecule such as CH2 groups. This is typically called a motif in that context. Both kinds of methods, so iterative and one-shot, have their advantages and disadvantages. Iterative models, for instance, can be pretty slow and more complex to implement, but they can generate much larger graphs as they keep updating the context. One-shot methods are pretty simple to implement, but can usually only generate smaller molecules. For this video series, I decided to try out one-shot generation as it's much easier to implement. As mentioned in the last video, the first attempt is to reconstruct the adjacency matrix. So let's have a look at the architecture of my model. The encoder are simply three graph transformer layers, which create embeddings of size 32. Then I split the network to output mu and sigma separately with an additional GNN layer. I chose a latent vector size of 8. It would also be possible to do that last step with a fully connected layer. In between these layers I apply batch normalization. Then for each node in the graph I sample from the latent distribution, which is defined by mu and sigma. That's currently the special part of this architecture, because later the plan is to have only one latent embedding, and here we have one per node. However, the layers that output mu and sigma are shared anyways, so each node passes through the same network. Later we could simply apply some pooling before passing through these layers, and then we have only one latent representation. For the decoder, I originally planned to use the inner product decoder, which I mentioned in the last video. However, I thought it's better to have another learnable component in this model. That's why I built all possible combinations of the adjacency matrix and passed them through another fully connected network. In my example, it has 3 layers with a size of 128. The output is simply if there is a connection between two nodes or not, so 0 or 1. For the future it will be easy to change that to also output different edge types, so not only this binary value. So one more remark here, so these combinations of vectors, they have a source node and a target node, and the prediction of the model is if there is a connection between these two nodes. So these combinations are supposed to stand for the adjacency matrix, so all combinations of potential connections. Of course, I faced some challenges when training this and I had to do further refinements. The first problem was that the predicted full adjacency matrix led to some inconsistencies because it is supposed to be symmetric. For a molecule, we have undirected edges, and therefore we know that the adjacency matrix will be mirrored along the diagonal. That, on the other hand, means that we can also consider this in the model. That's done by predicting only the upper triangular part of the matrix. We can also ignore the diagonal itself because we don't have self-loops in the molecules. And this significantly reduces the number of values we need to predict, so the number of combinations from source to target nodes. Still, the model had a tendency to always predict 0 because typically there are more zeros than ones in the upper triangular part. To account for this, I added a weight term to the binary cross entropy loss to consider this class imbalance. What happened is that the model now either always predicted 1 or always predicted 0 depending on the weight value. Finally, I calculated this weighted loss separately per graph, which means I had an individual weight factor depending on how many connections a graph had. With this, the model learned much better. By the way, another approach that I've also tried is negative sampling. That simply means we don't take all of the 0 values from the adjacency matrix, but only instead as many as edges we have. So the same number of ones with the same number of zeros. This way the loss term is also sort of weighted. So with these adjustments the training worked much better, but there was still one more thing because at the moment I had only a batch size of 1. And batching is usually used to speed up the training and smoothen the loss. And when I had this batch size 1, so I processed one graph after the other and then backpropagated the loss, then it led to a very unstable training. And therefore I implemented a simple batching strategy which simply loops over all graphs and then backpropagates the loss for the whole batch. The last thing that didn't work out of the box for my model is the balancing of the loss terms in the variational autoencoder loss function. As you know, the loss consists of a reconstruction term and a regularizer for the latent space. However, when training with this loss function, my model didn't learn anything because the KL divergence was somehow too restrictive for the model. To resolve this, I added a weight term to the KL divergence part, which is called beta here. Actually, there's also a paper about this called beta VAE, and in the paper they find a correlation between the size of the latent space and the optimal beta values. As my latent vector is also relatively small, I also chose a small weight for the beta, and the model suddenly started to reproduce the inputs. So that's the theory part behind everything I did, and now let's have a look at the code. So that is the project, and we see we have a train function for training the model, then this GVAE file, which is the model itself. The data set is the same as in the previous parts, so it's this HIV data set with those 40,000 molecules, I think. And I use this featureizer, which I also talked about in the last videos, to generate the same features as I used for the HIV prediction task. Then I also added this config file in which I specify the device, and at the moment it's CPU only because I have some issues with my GPU. However, there's no big speed difference between using GPU or CPU. Okay, now let's have a look at this train function, which is pretty simple. We'll load the train data set, the test data set, and the train and test loader with a batch size of 32. At the moment, I've limited the dataset to only use the first 10,000 molecules, and on the test set, I only test on the first 4,000. Then I specify the model, and also the loss function, the optimizer, and this KL divergence beta weight, which I just talked about. And I have this function run one epoch, which is called for the train and test section. So here is the train part. And every 5 epochs, I call this function for the test data. So I pass in the test loader, and here I pass in the train loader. And all this function now does is simply calculate or store some metrics, which I log later with MLflow again. And inside of this function, I just iterate over the specified loader, and then I pass in everything to the model, and I calculate the loss. Here it is. and I backpropagate it. Here we can see it, and calculate some metrics. So nothing fancy, it looks like in every other PyTorch implementation. So next, let's have a look at the model file. Here in the init function, I specify all of the layers we need. So we see a couple of encoder layers, and then this additional split layer which outputs the mu and sigma, which is another GNN layer. For all of these layers, I chose the transformer conf layer, and I pass in the edge dimension so that I can also use the edge features. I chose 4 attention heads and some other modifications. And then here are the decoder layers, are simply some linear layers, and in between I have batch normalization again. And the output is one value which will be used to specify if we have a connection or not. As you know, every PyTorch model calls the forward function when you pass in data. So if we have a look at the train function one more time, in this step where we pass in the node features, the edge features, the adjacency information, and the batch info, when that happens, all that happens is that we call this forward function. And here we have now 3 steps. So first we encode everything, and the output of this is the mu and sigma. So we have the information about the distribution. Then I call this reparameterization function, which does nothing else but sample using this mu and sigma. And then third of all, we have the decode function. And the output of this are the triangular upper part of the matrix and the logit values for that part. So let's quickly have a look at the encode function. It's pretty simple. All we do is we call these message passing layers, and in the last layer we separately get mu and sigma. And actually this is called log variance because the idea is to get more numeric stability by applying the log here, and later when we use it, so in this reparameterization function, we apply the exponential function to get back the original value for mu and sigma. So this is just a trick that is commonly done. So that's all about the encode function. We get those two as the output of the last GNN layer. And then I call this function, and this torch randn like does nothing else but sample. So this is this epsilon, if you remember from the last video. And now we have the mu, the epsilon, and the standard deviation, and all together we can calculate the sampled values. So the sampling takes place outside of the network so that we can backpropagate and don't have to handle this random node. And then we have the decoder, and I thought for the decoder, let's use the debugger to see what's going on because it will be much easier. And then we can step through the process in the decoder. So here we are at the breakpoint, and now let's have a look at this decoder function. So if we go here, we can see first of all that I implemented this for a batch of graphs, and we have this graph index which looks like this. So it's basically a map that tells us for each node, so each value represents one node in the batch, it tells us to which graph this node belongs. So these nodes all belong to the first graph, and these nodes all belong to the second graph, and so on. And using this batch index, I can now specify a graph mask. Let's quickly go in here. And this mask now basically masks out everything except for the graph in the batch I'm interested in. For the first graph ID, I only get the first graph and then the second one and so on. And in order to get the predictions, I first need to construct the input features. And I said I have all combinations for the triangular part of the adjacency matrix of source and target nodes. So I get, using this trio indices, which is a predefined function from Torch, I get the indices for the triangular upper parts. And so essentially in this graph, we have, so if we check this shape, we have 46 nodes. And this trio indices now gives me the edge indices for these nodes. And what I do now is I calculate, or I fetch the source features here and the target features for each of these source and target indices that I get out of this edge indices. So it sounds a little bit complicated, but actually all it does is, if we look at this, it fetches, so these are the features. This is the feature of node 0, and then we have again node 0, so several times node 0, and here in the end we have node 43, those are these two, and I have 44, that's the last one. And then I do the same for the target features. And so this is the second row, the first, the second, the third, and the corresponding node features. And now all I do is I concatenate them, so I append them. And now the graph inputs are simply, let's check the shape, 1035 nodes, or pairs of nodes, and each of them have a dimension of 32. And that's exactly what's going into my model. And here we simply pass through these decoder layers. And what we see in the end here is the edge logits. And we get for each pair a value. And when we later apply sigmoids, we get probabilities, and we can use them to say if there's an edge or not. So I hope that was not too confusing. There's quite some data wrangling or tensor wrangling you need to do. And now we can have a look at this utils function. We have also quite some helper functions here, but the main important part here is that we have the loss function. And now all the loss function does is, with those logits we got from the decoder, we can now calculate for each graph the individual loss. And all I do here is I get the target values, so the target triangular upper part of the adjacency matrix, and I get the predictions for this specific graph. So remember that these trio logits here are for the whole batch. That's why I need to slice them from the batch for a specific graph ID, and that's what's happening in those two slicing functions, which I have specified somewhere here. It's nothing fancy, it's just also calculating this graph mask and then using it to get the corresponding values in the batch. And I do that for the targets, for the predictions, and then I have the binary cross entropy loss here, and I calculate it between those two. And additionally, I specify a weight here, which says how many positive edges do we have in this graph. And that's all. And this gives me the graph reconstruction loss for one graph in the batch. So I append all of them to the batch reconstruction loss, which is then essentially nothing else but the average of each of the graph losses. And then I use the I calculate the KL divergence loss. This is happening somewhere here. And I got this formula from PyTorch Geometric. They've also implemented the KL divergence. And essentially this is the closed form for the KL divergence for normal distributions. And using that, I can then calculate the full loss, which is the KL divergence multiplied with this beta term and then the batch reconstruction loss. Now there's one more thing I do in this train function, and this is, so we have seen the loss function, we have seen the model. The only thing that is missing is this reconstruction accuracy function. And this is supposed to give me an accuracy value that tells me how many of the, or which percentage of the edges are correctly predicted. And for that, I have a function in this utils file, which I call reconstruction accuracy. It gets the triangular upper logits, and the workflow in this function is pretty similar as in the loss. So I slice everything for each of the graphs in the batch. And now what I do is I calculate the accuracy, and this is basically happening here. So between the batch targets and the actual predictions. And what I also wanted to know is if we are able to reconstruct with 100%, which molecules are those? And this is what's happening in this check trio graph reconstruction function. So I hope it's not too confusing, but essentially, so I loop over each of the graphs, and now I want to check if they are able to reconstruct with 100%. So I get the predictions here for this specific graph, I get the labels for this specific graph, and now I compare them with this torch equal. And if they are equal, then this means we have 100% accuracy. And then what I do is I generate the original molecule out of this. So basically I use the predictions to get back the molecule. And this is done in this graph representation to molecule function. And what I do here is I create an empty molecule, and then I add all of the atoms in the node types, and then I add all of the edges or bonds with this add bond function, which are in the predicted adjacency triangular upper. And what this gives me is a full molecule object. And what I do during training, if a molecule was successfully reconstructed, I print out the small string. And at the moment, I use bond type unspecified, and this will create these tildes in the small string because they are basically a placeholder that tell us there is some connection, but at the moment it's not sure which one. And for the next video, I plan to replace this with the actual bond type. And at the moment, I support these atomic numbers. And in the data set, so in this featureizer, every other atom type than those is specified with other. And I've mapped this other to a -1. And here in this function, I check if -1 is in those atom types. And if that is the case, I say, okay, it was successfully reconstructed, but there are some unsupported nodes because with this other, I cannot map it back to a molecule. So I will only generate the molecules which have these atoms. And by the way, hydrogen is implicit, so it's not specified here. And if that is the case, I can reconstruct the molecule in this function. Okay, and now I would say we can run the training so that we can see what's going on. And while this is running, we will see that it starts to reconstruct molecules, and the sizes of these molecules would get bigger and bigger. So it starts with reconstructing very small molecules, and then it should start to reconstruct larger ones. And those 300 steps here are 300 times the batch size 32, so that's my full data set. And at the moment we see no prints because nothing is reconstructed. In the meantime, we can have a look at the logs of previous runs. So let's have a look at MLflow here. We can see that I log several things such as the accuracy, the loss, the KL divergence, and I think this run was not very stable, but for instance, the number of reconstructed molecules is going further up. So the maximum number in this training was 971. So out of these 10,000, roughly 10% were reconstructed. And we can also have a look at the KL divergence. It's also decreasing, but I still have the feeling that some weird things are still happening here. And also overall that the KL divergence is too high. But this is something we will see in the next videos. And on the test data, so on new data that is unknown to the model, we get also an increasing number of reconstructed molecules. So here we have 4,000 molecules and 500 of them are successfully reconstructed. And now let's go back to the training. And as you can see, it started to reconstruct some molecules. So if we go back here, it starts with the smaller molecules. We have only 7 nodes here and 6 connections. And then it starts to get bigger and bigger. And as you can see here, it already reconstructed molecules with 18 nodes and 18 edges. And if we keep that training, it will reconstruct more and more molecules. And here I print the small string. So this is what happened in this utils function where I call this reconstruct molecule or whatever it's called. Here I print the small string, and that's exactly what we see here. Yeah, and as you can see, it starts to reconstruct everything, which is already a good sign. Already bigger molecules with 27 nodes. I think the largest one I've seen so far was, I don't know, 42 nodes or so. So this first training gives me the feeling that this is going in the right direction, because the GNN learns to compress the information into node embeddings and then is able to pick out two of these node embeddings and tell me if there is a connection or not between those. And it also works for larger graphs with up to 40 nodes. With this basis I've implemented It's Getting Serious now, because my next personal goal for this video series is to generate entirely new molecules until the next video. To make this happen, there are a couple of points on the agenda. First of all, I need to change the decoder to output different edge types. This should be fairly easy to implement. Then I need to make sure that the latent space is only one vector now. For this I need to sample the atom types as well as the number of atoms for the generated molecule. So after we've implemented that, we should be able to sample new molecules, and that will only work if the latent space is working properly, so if the KL divergence is small enough. When this works, we can then start to have a look at conditional generation, so that we don't produce arbitrary molecules, but instead molecules with desired properties. In our case, this means potential HIV inhibitors. And finally, I didn't optimize any hyperparameters yet, so that's also something we can try out. All in all, I plan to do 2 more videos on the generation part of this GNN series, and after that I will move on with the next topic. So that's all for today. Thanks for watching and have a great week.